Good afternoon to everyone. I am Dr. Karunesh Srivastava, and I am going to discuss some important topics that is related to optics, like diffraction and Fraunhofer diffraction and its types. So, in the previous lecture, I have already discussed some important topics and some phenomena of optics. Today, I will discuss the theories of lights, how different scientists have given different phenomena of lights. So, first of all, I will discuss the nature of light, and this was described by different scientists, and it has given by the different scientists, and they have given different theories. So, first of all, Isaac Newton has given the classical theory. After that, Huygens given the wave theory, Maxwell given the electromagnetic theory, and Einstein given the quantum theory. So, what is classical theory given by the Isaac Newton? The theory given by the Isaac Newton is according to this theory, the velocity of light in denser medium is greater than the velocity of light in rarer medium, but this is proved wrong later. So, I have already discussed in the previous lecture that or you have already studied about the velocity of light in different mediums. So, what is the effect of the medium on the velocity of light? If the light is moving from the rarer medium to the denser medium, that it is very obvious that the velocity of light will be less in the denser medium and greater will be in rarer medium. So, this theory was given by the Newton. According to this theory, the velocity of light in denser medium is greater than the velocity of light in rarer medium. So, this was wrong, and this theory also assumes that the source of light loses the mass as it emits corpuscles, but not such determinant in the source of light is detected. And this theory could not explain the phenomena of interference, diffraction and polarization of light, etc. So, this is the main drawback of this theory. So, I have already discussed this what is interference, what is polarization of light. Today I will also discuss this diffraction. So, these are the drawbacks of this Newton's theory. This theory could not explain the phenomena of interference, diffraction and polarization of light. So, for next theory was given by the Huygens. So, according to this theory, light is a wave which requires medium to travel called ether, but actually there is no existence of this medium ether. It fails to explain, this theory was unable to explain the polarization, photoelectric effect and Compton effect. Earlier I have seen that the Newton was also unable to explain the polarization, but this theory was able to explain the reflection and double refraction. So, this theory was unable to explain the polarization, photoelectric effect and Compton effect, but this theory was able to explain the concept of refraction, reflection and double refraction. So, this is the advantage of this Huygens wave theory on the Newton's theory. So, it also explains the transverse nature of light, but fails to explain why light has no longitudinal component. So, as I have already discussed this, the nature of light in the previous lecture. So, you can see from there Maxwell electromagnetic wave theory. So, up till now we have seen that the Newton's theory was unable to explain the phenomena of light like reflection, refraction and polarization, but the Huygens wave theory was able to explain the polarization, was unable to explain the polarization, but able to explain the reflection, refraction and double refraction. So, next theory was given by the Maxwell, that is electromagnetic wave theory. The electric and magnetic field in an electromagnetic wave is continuously varying with respect to time and space. If I say, what is electromagnetic wave? Electromagnetic wave is the composition of electric field and magnetic field, or you can say this is the composition of electric wave and magnetic wave. So, how will you explain this? What is electric wave and what is magnetic wave? So, if suppose if the electric wave is propagating in x direction, then the magnetic wave will propagate in y direction, and the combination of this electric and magnetic wave will propagate in z direction. Or you can say these waves are perpendicular to each other, or you can say these waves are transverse in nature, they are perpendicular to each other. So you can easily say that if this is propagating in x direction, this is propagating in y direction, the electromagnetic wave will propagate in z direction. So the electric and magnetic field in an electromagnetic wave is continuously varying with respect to time and space. So you can consider the electromagnetic wave as a function of time and the function of space. At any instant, electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of light. The magnetic wave is transverse wave. At every point in the wave at a given instant of time, the electric and magnetic fields strengths are equal, and the velocity of propagation of electric and magnetic wave depends on electric and magnetic medium, magnetic properties of the medium. So the main drawback of this theory is it failed to explain the photoelectric effect and Compton effect. Electromagnetic theory also failed to explain the black body radiation, but you can see here that Huygens was unable to explain, Huygens theory was unable to explain the phenomena of polarization, photoelectric effect and Compton effect, but this theory was able to explain the polarization, and this theory was unable to explain the photoelectric effect and the Compton effect. So in Newton's theory we have seen that the Newton was unable to explain any phenomena of the light. Huygens was able to explain the some phenomena of light, and Maxwell was able to explain the polarization of the light. Now next theory is the Planck's quantum theory. So according to this theory, light energy is released from the source directly in the form of energy packets of specific frequencies called photons or quanta. Photons are propagated as waves and if necessary interact with the matter as particles. This theory explained the phenomena of Compton effect, photoelectric effect and black body radiation. So this is the advantage of this Planck's quantum theory over the Maxwell theory, that Maxwell and Huygens theory. Maxwell and Huygens was unable to explain the Compton effect and photoelectric effect, and this black body radiation was Maxwell was also unable to explain this black body radiation. So the main drawback of this theory is it could not explain how it is connected with the wave nature of the light. So so these are the theories, and these are the advantage and disadvantage, drawback of these theories. So the classification of different phenomena based on theories of light. So these are the theories of light. So we can classify the different phenomena on the basis of this theory. Wavelength, color, polarization and diffraction comes under the category of wave theory, and interaction of light with atoms comes under the category of quantum theory of photons. So if I am discussing about the wavelength, color, polarization and diffraction, then it will be the part of this wave theory, and if I am discussing this interaction of light with atoms, then it will be the part of quantum theory of the photons. So we have seen this the different theories of light, in which we have seen that what are the main drawbacks, what are the advantage of these theories. So now you could be able to explain the drawback. You will be able to know the explanation. You will be able to know the drawback of these theories as well as the advantage of these theories. So the main drawback of main drawback of these different theories has been explained in the previous slides. Now the next topic is diffraction of light. So first of all, what is diffraction? The phenomena of bending of light around the sharp corners and spreading into the regions of geometrical shadow is called the diffraction. So, the light waves are diffracted only when the size of the obstacle is comparable to the wavelength of the light. So, this is the condition for diffraction. So, how will you define this diffraction? The phenomena of bending of light round the sharp corners and spreading into the regions of geometrical shadow is called the diffraction. The light waves are diffracted only when the size of the obstacle is comparable to the wavelength. This is the condition for the diffraction. So, there are two types of diffraction, Fresnel diffraction and Fraunhofer diffraction. So, what is Fresnel diffraction? It is the type of diffraction that takes place at a slit when a source of light lies at the finite distance from it. And what is the Fraunhofer diffraction? It is the type of diffraction that takes place at a slit when a plane wave front is incident on it and the wave front emerging from the plane from the slit is also the plane. For this, both the source and the screen should be at finite distance from the slit, and the Fraunhofer diffraction can be easily observed in practice. So, this is the setup for this Fraunhofer diffraction. In this case, the source of light or screen or usually both are at finite distance from the diffracting aperture or obstacle. In this case, no lenses are used and the incident wave front is either spherical or cylindrical. So, this is the condition, the incident wave front is either spherical or cylindrical, and in this case no lenses are used. So, the first condition for the Fresnel diffraction is the source of light or screen should be at finite distance from the diffracting aperture. Next is Fraunhofer diffraction. So, in this Fraunhofer diffraction, the source of light and screen are effectively at infinite distance from the diffracting aperture or obstacle. So, this is achieved by placing the source and screen in the focal planes of two lenses. In case of Fresnel diffraction, source and slit or source and screen should be at finite distance. So, the second the condition for this is achieved by placing the source and screen in the focal planes of the two lenses. The incident wave front is plane, this is the condition. Fraunhofer diffraction is a limiting case of the more general Fresnel's diffraction. So, you can see here we are using here different lenses, but they are in the same plane. So, you can see here we are using here the point source and we are getting here the output. So, at the center we are getting the maxima and we are moving away from the center in y direction, then we are getting the minimas, or you can say the secondary maxima and minima consecutively. And this Fraunhofer diffraction is much easier to calculate the intensity distribution of a Fraunhofer diffraction. So, you can easily calculate the intensity of the wave, intensity I, that intensity is directly proportional to the amplitude square. So, you have to calculate the amplitudes by using the vector analysis or any method, so that you can calculate the amplitude. After calculating the amplitude, you can get the intensity by simply squaring the amplitude. This is the experiment for this Fraunhofer diffraction at a single slit. So, it is clear that there is a source and there are a slit. The distance between the slit, the gap between the slit is E, and this is the diffraction angle delta. So, let a parallel beam of the monochromatic light of wave length lambda incident normally upon a narrow slit of width ABE. So, this is the width between the slits, narrow width between the slits. So, you can say this is the AB is equal to E. Let diffracted light be focused by a convex lens L. This is the convex lens L on a screen XY placed in the focal plane of the lens. The diffraction pattern obtained on the screen consists of a bright band having alternate dark and weak bright band, decreasing intensity on both sides. So, you can see here when you will get the output on this screen, it will appear the maxima, as I have already told you that the maxima will appear at at the center, and or you can say central maxima will appear at the center, and minima or secondary maxima will appear at the other side of the origin on y axis. So, in terms of the wave theory, a plane wavefront is incident on the slit AB. According to this Huygens principle, each point AB sends the secondary wavelet in all direction. The rays proceeding in the same direction as the incident rays focused at O, while those diffracted through an angle theta are focused at P. So, you can see here in this figure that AK is equal to BK. So, from this figure it is clear that this is the distance A. So, AK will be equal to, this is the center, then AK will be equal to BK. So, same has been written here. So, let us find out the resultant intensity at P. So, we are going to find the resultant intensity at this point P. So, for finding this resultant intensity, what you have to find? We have to find the path difference. So, for finding the path difference, we will see from this figure the distance travelled by this wave and the distance travelled by this wave. Or if I am considering this wave, then we can consider this wave at this point P. The same wave propagating in this direction and the same wave is coming to this point P from this direction. So, what will be the path difference between these two waves? So, for finding the path difference, we will draw the from point A and point B. So, this is the path difference you can see here. So, this is the path difference. So, what will be the path difference? The wave travelling from this point to this point and from this point to this point. So, the distance between this and this point, the wave is travelling in this direction, the wave is travelling in this direction. So, this distance travelled from A to P and K to P is same. The only difference is this BK. This will give the information about the path difference. So, how will you calculate this path difference? This is E and this is the BK. So, you can use this theorem, sin theta is equal to BK by D, BK by E. So, this will give BK, the value of BK is nothing but E sin theta. So, you can see here this is nothing but E sin theta. Similarly, you can find the path difference. So, path difference is nothing but 2 pi by lambda into, this is the path difference. Similarly, you can find the phase difference. Phase difference is nothing but the path difference multiplied by 2 pi by lambda. So, once you have find this path difference, then you can usually find you can easily find the phase difference. So, it will be equal to 2 pi by lambda into path difference, 2 pi by lambda into E sin theta. Let the width AB of the slit be divided into n equal parts. Then the amplitude of vibration at P due to the waves from each part will be same as A. So, what will happen? This is the path difference, this is the phase difference. So, how will you find the phase difference for n number of slits? So, you can divide this by n and you will get here d is equal to 1 by n 2 pi by lambda E sin theta, and the resultant will be equal to R is equal to A sin n d by 2 by sin d by 2. This is the formula for resultant of the n number of n vectors, and they are deviating with the phase difference or with the angle d. So, it is the standard formula, you can remember this. R is equal to A sin n d by 2 by sin d by 2. Now, I am going to put this value of d in this formula, A sin pi E sin theta by lambda sin pi E sin theta by n lambda. So, you can consider this pi E sin theta by lambda with you can replace this by another variable, this is alpha. So, you can write here R is equal to A sin alpha by alpha sin alpha by n. If this alpha by n is small, then sin alpha is nearly equivalent to alpha. So, you can write here alpha by sin alpha by n is nothing but alpha by n. So, this resultant will become R is equal to n A sin alpha by alpha. So, as n tending to infinite, A will be tending to 0, but the product remains finite. You can see here. So we are considering here because we have we have considered that this is a small. So if this is a small, this factor can become a small if this is infinite, and the numerator is 0. So this is the method. How can you find the resultant of the path difference, phase difference, and the resultant of the resultant vector of the from the Fraunhofer diffraction? So this is the procedure. How can you calculate? You have to remember this formula, or you can derive. If you want, you can derive this formula by using the vector analysis. You can easily derive this formula, but at this stage you can remember for finding the amplitude of the nth vectors. Now, so next topic is diffraction grating. So an optical element consisting of a large number of equidistant parallel narrow slits of equal width separated by equal opaque portions is known as diffraction grating. The plain diffraction grating is a plain sheet of transparent material on which opaque rollings are made with a finite diamond pointers. The distance between two adjacent slits is comparable to the wavelength of the light for which it is designed. So up till now you have seen that the distance between two adjacent slits is comparable to the wavelength of the light. In the previous slides I have already discussed this, where we are putting this size of the obstacle near to the wavelength of the light. The distance between two adjacent slits is comparable to the wavelength of the light for which it is designed. The modern commercial form of grating contains about 6,000 lines per centimeter. So types of grating, diffraction grating. There are basically two modes of operation: transmission and reflection. In transmission grating, light passes through a material with grating written on its surface, and the lines are drawn on the transparent glass sheet. So this is the method how can you get transmission grating. And the reflection grating, light in the reflection grating, light is reflected from a material with a grating written on its surface. So in this case, in the case of reflection grating, we are using a mirror. So lines are drawn on a mirror. So in a case of transmission grating, for transmission grating, what is the difference between transmission grating and reflection grating? In transmission grating, we are using a transparent glass sheet, and we are drawing the lines on this transparent glass sheet. But in case of reflection grating, we are using the mirror for reflection purpose. Now, what is transmission? Transmission diffraction grating is similar to the Young slit experiment, except instead of having two slits, there are many equally spaced lines ruled on a glass slides. Each line diffracts the light source, causing a diffraction pattern. The diffraction pattern caused by the grating pattern is usually much more widely spaced, while the double slit experiment pattern normally is a series of closely spaced bright fringes. The grating pattern therefore is easier to use, as it can give more accurate results in most occasions. So if you are using this transmission grating, so we can use this grating pattern and in this diffraction transmission grating, each line diffracts the light source, causing a diffraction pattern, and the diffraction pattern caused by the grating pattern is usually much more widely spaced, while the double slit pattern normally is a series of closely spaced bright fringes. So this is the figure in which you can see how can you get the transmission grating. This is the glass sheet in which number of lines are used, and the light will pass through this slit. So after passing from this screen, from the source light we are using a slit. This is the single slit, and here we are using the for diffraction grating we have used the transparent sheet in which number of lines are used. So on the screen you can get the different colors of lights. When a narrow beam of monochromatic light is directed normally at a transmission grating, the beam passes through it and is diffracted into well defined direction. So the direction of, if I am what will be the phenomena for this? If I am using the slit in y direction, then it will propagate, then it will pass only the vertical waves. If I am using the slit in the horizontal direction, then it will pass the horizontal waves. And similarly in the diffraction grating, if I am using the same, then we are getting the y axis waves. So this is the transmission grating. At again, how will you get the maxima and minima at the point P? So here the in this diagram we are using the plane transmission grating, and a monochromatic light source is used to record this pattern. So you can see here the light is passing from this point A, point B, point C, and number of lights are passing, and this is passes through a lens, and at this point P1 we are getting the output. So in this phenomena you can see here, so how will you calculate the intensity of the light at this screen? So for calculating the intensity of light, we have to find the resultant amplitude. As you know this, the intensity is directly proportional to amplitude square. Or before finding this resultant of the amplitude, you have to find the path difference, phase difference, and principal central maxima or minima, central maxima and secondary maxima or minima. So this so these things you have to find for calculating the intensity at point P1. So as I have already discussed, how will you find the path difference, how will you find the phase difference? After finding the path difference, you can use similarly use you can easily use the formula 2 pi by lambda into path difference for finding the phase difference. So you can get here phase difference. After getting the phase difference, you can calculate the intensity after finding the resultant. So in the transmit, the result that we get is a series of bright spots on a screen which are called the maxima. The one in front of the light source is called the maxima and it is the brightest. The others are numerically numerical order. So first maxima is on other side and the zeroth on another side. So and the width of the grating element is A plus B. You can see here, this is the width of the grating element. Now what is grating theory? So diffraction grating is an arrangement equivalent to a large number of parallel slits of equal widths and separated from each other by equal opaque spaces. So you can see here I am using the n number of slits, and these slits are spaced by E plus D. So E plus D is the distance, this is the opaque of the slits, and the distance between the slit is D. So you can see here the distance between the slit is D and the opaque is E. So again we have to find the we have to find the intensity of this. So first of all we will find the path difference. So how will you find the path difference? This is E plus D, and what will be the path difference? Path difference will be given by this as 2k. So what will be E plus D is called the grating element, and what will be the path difference? Path difference is nothing but, so you can see here the path difference is nothing but here not written. So you can see here E plus D sin theta, and you can find the points in two consecutive slits separated by the distances E plus B, E plus D is called the corresponding points. And let a parallel beam of monochromatic light of wavelength lambda be incident normally on the grating. So after an incident normally on the grating, we can find the Fraunhofer diffraction at a single slit. The wavelengths from all points in a slit diffracted in a direction theta are equal to the wavelength amplitude A sin alpha by alpha. So from where we got this, we have already I have already derived this. R is equal to A sin alpha by alpha. I am using this formula. A sin alpha by alpha, where alpha is equal to pi by lambda E sin theta. If n be the total number of slits in the grating, the diffracted rays from all the slits are equivalent to n parallel slits. and it will be the middle points of the slits. So what will be the resultant of the amplitude for this? R will be equal to A sin alpha multiplied by this. From where we got this? I will discuss this in next lecture. How will you get this resultant amplitude after from this figure? So this amplitude has been derived from the Fraunhofer diffraction. So you know this, and I will multiply with this, and where t is equal to pi by lambda e plus d sin theta. So after getting this R resultant amplitude, I can find the intensity, and after that I can find the maxima and minima at different points. So this is all about for today. In the next lecture, I will discuss this. I will continue with this topic. Thank you.